Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Step 1 concept. A chiral molecule is one that is non-superimposable on its mirror image. It lacks an internal plane of symmetry or any improper rotation axis. A molecule can be chiral due to stereocenters, axial chirality, or planar chirality. Step 2 analyze molecule I, butane, 2,3-diol, anti-thiodiestereomer. Molecule I shows butane, 2,3-diol where C2 has O on a wedge and C3 has O on a dash. This represents the 2R, 3R or 2S, 3S configuration, the anti-diastereomer. Because the two stereocenters have opposite configurations relative to a meso possibility, this is actually the anti or thrio form. For butane 2,3-diol, the meso form has an internal plane of symmetry, same configuration at both centers in a way that allows superimposition, while the R, R and S, S forms are chiral. Looking at molecule I, the O groups are on opposite faces, one wedge up, one dash. This is the anti-arrangement C2, R and C3, S or C2, S and C3, R. This I is the meso compound, achiral. Weight re-examining, in butane 2,3-diol, the meso form has one O up and one O down, anti, giving an internal mirror plane. The chiral forms are R, R and S, S, where both O's are on the same face. Molecule I shows one O wedge and one O dash is equal to anti is equal to meso is equal to achiral. Molecule I is not chiral. Step 3 analyze molecule 2, butane 2,3-diol, SYN erythrodiastereomer. Molecule 2 shows both O groups on wedge bonds, same face. This is the R, R or S, S configuration of butane 2,3-diol. This diastereomer does not have an internal plane of symmetry and is chiral. Molecule 2I is chiral. Step 4 analyze molecule 3, cyclopropane with CH3 and O substituents. The structure shows a cyclopropane ring with CH3 at the top carbon, CH3 at the bottom carbon, 2 O groups on the left carbon, or 1 O each on adjacent carbons on the left and H atoms on the right. This is 1,2-dimethyl 3,3. Rereading, the circle representation shows top is equal to CH3, bottom is equal to CH3, left top is equal to HO, left bottom is equal to HO, right top is equal to H, right bottom is equal to H. This is a 1,2 disubstituted cyclopropane with O and H on one carbon, upper left and lower left being two different carbons, CH3 on top and bottom carbons. The molecule has two stereocenters on the cyclopropane ring. The key question is whether it has an internal mirror plane. Given that both O groups are on the same side and both CH3 groups are on opposite positions, this molecule lacks a plane of symmetry and is chiral. Molecule 3I is chiral. Step 5 analyze molecule 4, bicyclobutane with methylene bridge. This is bicyclo 1.1.0 butane with a bold wedge. The molecule appears to be a bicyclic system. Bicyclo 1.1.0 butane itself has a plane of symmetry and is achiral. The bold wedge shown may represent the geometry of the fused ring rather than a stereocenter. This molecule is achiral. Molecule 4 is not chiral. Step 6 analyze molecule V, spiro compound. This is a spiro compound with two 5-membered rings. Spiro compounds can be chiral due to axial chirality, spirochirality, even without classical stereocenters, but only if the two rings are differently substituted. The compound shown appears to be spiro 4.4, nona 1,6 diene or similar, with double bonds in specific positions. If both rings are identical, same substitution pattern, the spiro center is not a stereocenter. From the structure, both rings appear to be cyclopentene rings, with one double bond each, making them identical, thus the molecule has a plane of symmetry and is achiral. Molecule V is not chiral. Step 7. Conclusion. Chiral molecules 2 and 3. This corresponds to answer choice C. Why other options fail? A. I and 3. Molecule I is the meso-achiral form of butane 2,3-diol. B. I and V. Both I and V are achiral. D. 2, 3, 4. Molecule 4, bicyclobutane, is achiral due to molecular symmetry. Therefore, the correct answer is C. Therefore, the correct answer is option C.